Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about a very useful theorem to make inference in linear regression, the orthogonality theorem. This theorem will allow us to have the necessary tools to derive distributions of test statistics that we're going to be using to carry out hypothesis tests in linear regression. First, let me state the theorem. If we go to our lecture notes, you'll find it there, the orthogonality theorem. Before we state the theorem, let me remind you that an orthogonal matrix is a matrix such that A inverse equals A transpose. Now, let's talk about the statement of the theorem. So what we have here is a random vector with n components, and each individual component has a normal distribution with mean 0 and variance sigma square. And they are independent of each other. Make sense? Next, what we do with this random vector, or with their components, is we define a transformation, W. And that transformation is just the multiplication of a matrix A, but a very special matrix A. A is an orthogonal matrix, so A, the matrix product between A and Y, yields that transformation W. Okay? And the important conclusion of the theorem is that the components of W, the Wi's, are again independent, and they inherit the distribution from the Y's. They have a normal distribution, same mean, same variance, sigma square. Make sense? Okay. Now, let's apply this theorem to a particular situation. Let's talk about an example. By the way, in this video, we will just apply the theorem. However, in our lecture notes, we show that this is the case, that the conclusion of the theorem follows using the multivariate transformation method, using multivariable calc, basically. Okay. So, in this particular example, we have a vector with 3 components, a random vector with 3 components, y1, y2, y3. The conditions of the orthogonality theorem hold. That is, these guys, these components, have a normal distribution with mean 0 and variance sigma square. And we defined a transformation, W, like this. It's the matrix multiplication between matrix A and our random vector Y. Okay. The matrix A is defined like this, and what we want to do is showing that the components are independent, normally distributed, with mean 0 and variance sigma square. So if we want to apply the orthogonality theorem, all we have to do, right, is showing that A is an orthogonal matrix, right? And as we said, an orthogonal matrix is one such that A inverse equals A transpose. So if we can show that A is an orthogonal matrix, we're done, right? We're just applying the orthogonality theorem. Well, let's use R to show that that's the case. But before we do that, let's just have a very clear in our minds what the components look like, what the components of this transformation look like. So we have a matrix, a 3 by 3 matrix. You guys agree? A is a 3 by 3 matrix. It's defined, the first row is 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3, and then times y, but the inner product, right? So turns out that the first component, w, because see, when you do the analyze the dimensions of the components, this is 3 by 3, this is 3 by 1, then the resulting transformation is going to be just a 3 by 1 matrix W, where the first component is going to be, let me show you, first row times vector y, right? So it's going to be y1 over the square root of 3 plus y2 over the square root of 3 plus y3 over the square root of 3. So that would be w1. And if you do the same with the second row of the matrix A, you end up with the second component. So it will be negative 2 times y1 plus y2 plus y3, all divided by the square root of 6. That would be w2. Finally, w3. Right? It would be 0 times y1, then we have nothing, minus y2 plus y3 divided by the square root of 2. That's what we have here. Okay? So these guys are the components of this 3 by 1 random vector w, which is the result of this transformation. Okay? Now, we said that we want to apply the orthogonality theorem. Since y1, y2, and y3 are normally distributed, they're independent, they have means 0, variances sigma square, each of them. If we could show that this 3 by 3 matrix A is an orthogonal matrix, we are done. And to do that, we are going to be using R. So let's define the first transformation here. Let me clear my console here. Yeah. Okay. So W1 will be just a matrix. And let me define it. It's going to be 1 over square root of 3. 1 over square root of 3 and 1 over square root of 3. Right? Okay. So we have just one row, that is the first row of the matrix A, right? One row, 3 columns. What we have here is W1, first row here. Okay? That's what I mean by that. Okay. Let's make sure that we have what we want. Looks right. Okay. W2. It's going to be similar, right? But instead of having, we will have to change it slightly, right? Instead of having here A1, we're going to have a -2 here. We have square root of 6. We have a 1, that's okay, but we have a square root of 6, and we have another square root of 6, because that's the second row of that matrix A. Okay? Okay. And that would be the second W. Okay. Now W3 it's going to be the first one is a 0. Next one is -1 over the square root of 2. Next one 1 over square root of 2, right? Because we have this here. Okay, I'm just using the W lowercase w's to refer to the row that defines well, the rows, the 3 rows that define our matrix A. Okay? Okay. Now let's combine these rows to create a matrix A that is the one we want. Since I'm thinking about these guys, right, as rows, let me paste them as rows. Row bind, because you guys know that R by default thinks of vectors as columns, and in this case I want these guys to be pasted by row. Okay, so row bind, that's the function that we're going to be using to paste W1, W2, W3. A has 3 rows and 3 columns. Let's make sure that we have what we want. Yeah, it looks fine. Okay, now let's apply our theorem. Again, all we have to do is showing that A is orthogonal, and to do that all we have to show is that A inverse equals A transpose. So let's find the inverse of A. That's the inverse of A. Let's find the transpose of A. Guess what? These guys are the same. So nice. We're done. Since A inverse equals A transpose, we are done. We are done. We are applying the orthogonality theorem. That's it. Okay, let's recap. What we did today in this video is we applied a theorem. That theorem states that if we have a random vector y formed, well, a random vector y that contains n components, y1, y2, up to yn, where the y's are independent and normally distributed random variables with mean 0 and variance sigma square, and we define a transformation like this W equals A times Y, right, where A is an orthogonal matrix, then it turns out that the components of the transformation W are going to be also independent and also normally distributed with the same mean as Y, 0, and the same variance as Y, sigma square, well, the components of Y. Okay, so this result will be very useful in the near future to carry out hypothesis tests in linear regression. We will refer to this theorem, to this result, as the orthogonality theorem. Well, that's it for now. Take care and keep working hard. See you next time. Bye.